projects? All right. How many have come here to become buzzword compatible? All right. So this is our goal today. If you allow me, I would just introduce myself. I'm Vladimir Bekvansky. I'm running a company which is doing custom development and training. We do typically highly scalable systems which usually have big data backends. And our applications lately are applications in healthcare, Internet of Things, in financial space, and we also help implementing big data systems in organizations. So you have my coordinates on Twitter and LinkedIn. You're welcome to connect. So I'm sure you didn't come all the way here just to watch in some PowerPoint presentations. So I figure out I'm going to draw some pictures for you. So when you open any kind of tutorial or a book or an article on big data, you're going to be greeted with a diagram that looks like this. So there will be some coordinates, and they will tell you, OK, this is the time. And then this is the volume of data that we have. And then you will see a curve that looks like this. And then they will tell you, by 2013, we are going to have 719 yottabytes of data. And you really don't know if this is really much, or should we have more, or should we have less. And that really does not matter. We really don't have a good intuition when we deal with such large numbers. But what is important is where we are in this curve. And we are somewhere here. So we are going to see a tremendous growth of data, and the question is, how are we going to deal with that? So one of the natural questions that you may have, and that you should have, is, so what is wrong with our traditional database technologies? What is wrong with relational databases? And why is that we cannot handle such loads with relational databases? So if you put relational databases in this picture, together with the progress that we see in our infrastructure, you will see that things behave like this. So imagine if you are looking into the cost of accomplishing some performance. And we are going to put here capability of our systems. We are going to see that the capability of our systems is growing like this. So it is growing fairly linearly. And this is basically our infrastructure. So it is growing linearly. This is good. So for example, if I need 4 terabytes of disk, I know this is going to be roughly 2 times more than 2 terabytes of disk. We don't see much improvement when it comes to the clock speed of CPUs, but we can put more CPUs and they have more cores. So particularly in cloud settings, these things are growing nicely in a fairly linear fashion. And then you put into this picture the expenses that we have with our relational databases. And you're going to get a curve that looks like this. So in the beginning, you may say, well, it is fairly easy to start. So I can start somewhere here with something like MySQL, small open source system. And then your appetite grows, and you say, well, now I need to go with maybe SQL Server. When that is not enough, then you are here, and you're saying, well, I need to use Oracle or DB2. And eventually, the volume of data increases even more. Then you get Teradata system. And then after that, there is pretty much nothing more to buy. And we see this exponential cost that is associated with relational databases. And one of the reasons for that is that relational databases are not really good when it comes to partitioning the loads across many machines. So they prefer to run on one large machine. And we see limits with that. So when you put yourself now in a position of companies like Google and Yahoo in the late 90s, they were looking how are they going to store the data into the web system that they are dealing with. And they figure out that the relational databases are going to fail for 2 reasons. One is that there is the whole range of data that is basically out of reach. You simply cannot store these volumes in relational systems. And the other problem that we have is that even if you manage to squeeze some amounts of data, it is going to be really expensive. And that was really the motivation for creating a whole range of new data technologies, particularly big data and NoSQL technologies. And what we expect to see in systems like this is a nice linear dependency, which is closely matching the situation that we have in our infrastructure. So this red curve is what we expect to see with big data and with some of the NoSQL stores. So that is the key reason why relational stores are not a good match, and we need to look for some other solutions. So what are these other solutions? How are we going to deal with splitting the loads on multiple machines? Well, the most significant thing that happened in that space is the revival of something that is known as the MapReduce. And the MapReduce is an algorithm that enables you to do the processing across many machines. It is a very primitive algorithm, and it enables you to split your load across multiple machines. It consists of two phases. We do some transformation of data, which is the map, and then you do the reduce, which is bringing the data together. And the MapReduce in several variations is a foundation for most of the big data systems that we have. So the second part that we need to have is, imagine that we have processing that is now happening on multiple machines. So we have more data than can fit into one single machine. So I'm going to make a couple of clones of this. And imagine that we have a fairly large file. The file is so big that it cannot fit into a single machine. So the idea is now that we are going to take this file and we are going to split it into sections. And I'm going to name them 1, 2, 3, 4, 5, and so on. And then I'm going to take these pieces of data and I'm going to put them into these machines. So I'm spreading the fragments of this file across multiple machines. And you can imagine here we have our fragment 1, 2, 3, 4, and so on. So when we split this data, this could work. We process each of the parts of this file on a different machine. But when you have hardware, you know what will happen with this hardware sooner or later. Something will die. The CPU will burn out, the power unit will go away, you will lose a machine. And you definitely don't want to lose the fragments of data that you have. So how do we deal with fault tolerance? One of the old recipes that always works is redundancy. So we are going to take each piece of data and we are actually going to store it in multiple copies. So we will have each of these fragments stored in multiple locations. So for example, I'm going to have this fragment number 1 stored on this machine here, number 2 over here, 3, and so on. And actually, I'm going to look for the redundancy, which is by default factor 3 times. So this is the normal, and redundancy factor of 3. Now, when you have all these things that are split across these multiple machines, you need to keep track of what is where. You need something like a table of contents. So where do you put that? So normally, this is done by placing it on a separate machine that is typically a bit more powerful and a machine that has more memory. And we call this special machine the master node. So the master node will have one part inside, which is basically your table of contents. It's here inside, and it keeps track where are these different pieces of files in our cluster. And this part has a particular name. It is called the name node. It's like a table of contents. And you prefer to keep it in RAM because you always need to access the information where are your files. So this is the master node. So we have the cluster, we have the data nodes that store the data, we have the master node that is keeping track of the processing. And now something that is really interesting, in this MapReduce algorithm, we have the functions that are doing the processing, And the question is, how are we going to process this data? You know, in traditional systems, what do? You have your data in the database, then you run some query, you bring the data into your application, do some transformation, and then you send data back to the data store. Well, this is not such a good idea if your data is in petabyte size. And the saying is, you don't move petabyte to the program, you move program to the petabyte. So what we will do here is we are going to take our programs, our little MapReduce functions, and we are going to place them on each of these data nodes. So the functions for processing will be happening on these machines. So this is where we have our functions for map and reduce. So basically you deploy your programs on the machines, and here is the fascinating thing that will happen here. And that is this MapReduce functionality is going to process only the files that are local to the machine. So they are never going to cross the machine boundary. And this is actually really good because you have the local data access, and this is fairly fast. Between map and reduce, there is one phase that is the natural part of this workflow. And this is the part that is called shuffle. So in your MapReduce algorithm, you will have 3 key phases. One is going to be the map, the second is shuffle, and the third one is reduce. So data goes from map into shuffle. You exchange the data between the machines, and then finally you have a reduce. Now shuffle happens to be always the same, and it is done by the framework. And one of the tremendous benefits of systems like this is that when we are writing our systems, we only need to write the things which are these map and reduce functions, and the rest is handled by the framework. Now, when you take this combination of MapReduce and you put it together with this reliable storage, then you get a system that is known as Hadoop. So Hadoop is a combination of this reliable storage that is known as HDFS, which is the Hadoop Distributed File System. And it is a fault-tolerant system. It emerged with Hadoop, but today we use it with various other data processing frameworks because it provides us with good performance for storing the files across many machines. There is fault tolerance, there is redundancy, so we don't have headaches when something dies. And one of the other nice things that we have in HDFS is even ability to self-heal. So if the node dies, you take it out, you put a new node inside, and then the system will send the data from other nodes, and you are going to recover the data that were originally vanished from the node in question. So this is the Hadoop. And you see combination of MapReduce, combination of HDFS. In the beginning, MapReduce and HDFS were tied together, and later they were decoupled, and that resulted in one part of Hadoop, which is called YARN. YARN stands for yet another resource negotiator, and it is just part of infrastructure that is separating our processing that we have here. To move it a little bit. Then we have the YARN as a layer underneath, which is the resource manager. And then eventually at the very bottom, you're going to find the HDFS as a simple storage area. So that is your typical Hadoop representation. So that was the state of the art for some years. But if you think about the processing that is happening here, you're going to find that there are some potential problems. First, when you look into this processing that we have with these 3 phases, map and reduce, there is a shuffle in between, map, shuffle, and reduce. The data is stored in some file system. And basically what we need to do when we are doing the processing, the map is going to do some reading. Then when map is done, its intermediate results will be written to the data store. Shuffle is going to read something, then it will send it through the network, and then eventually write it down. And then we have, again, a read from the disk and a write to the disk. So original Hadoop is very disk intensive. And we know that too much input-output is not good for performance. So after the Hadoop was designed, somewhere around 2009, we have seen the work from a UC Berkeley lab for machine learning. And they have been looking how to improve this processing scheme. And they have decided to think about how our computer is going to look like in the near future. And one thing that they have figured out is that you are going to have plenty of RAM. So you're going to have quite a bit of RAM. And you can imagine with this RAM, we are going to get our initial data from some data store. And then we are going to move it into the RAM. And now we are going to have these different data structures that reside in RAM, you see. And we are going to keep them there. We are assuming that the RAM is going to be plentiful. And then we can run various programs that will be processing the data in memory. So we have these programs. So this is my program. And it is going to manipulate the data that I have in RAM. So I don't need to constantly read and write from the disk. And this is going to give me a good performance. So the typical performance that you are going to see as an improvement of such a measure is going to be somewhere around 100 times faster than original Hadoop. And this is now getting really interesting. One of the things that this scheme is dealing in a different way is fault tolerance. You see, Hadoop, in order to achieve fault tolerance, is always writing to the disk. So if something dies, you go and read it from disk, and that is how you recover. But what this group has figured out, that it is sometimes faster to keep track of what are you doing. So you are going to create a set of steps that you remember. So you will do a read from some data store, and you will have various steps that you are using to process your data. And now if everything works fine, then you are just going to collect the result. If something goes wrong, you are remembering these steps in some persistent storage, and then you are going to replay the steps. Because data is in memory, redoing the step is often faster than reading the data from the disk. And that led to a new concept which is called RDD, which stands for a Resilient Distributed Data Set. And this is the foundation of the system which is called Apache Spark. Spark will typically keep the data in the disk storage, which is usually HDFS, but also it can be a different type of database. So the system is very versatile in that regard, brings in the data into the memory, and this is where you do the processing. Now, this group dealing with machine learning, they are very interested in running iterative processing. So you have programs that are constantly manipulating and updating this data that we have in the memory. By the way, I have seen some of you are taking pictures of this. Don't worry doing that. I will be saving all of these drawings that I'm doing. I will create a little PDF booklet at the end, and you can just send me the email and I will reply with the slides. And you have a conventional set of PowerPoint slides also for this talk. So this is Apache Spark. And the key thing that we have with Apache Spark is significantly improved performance. And people usually expect around 100 times. In reality, it is smaller because Hadoop has also made notable improvements in performance. So in reality, the numbers are typically less, but still Spark gives us a significant improvement in performance. So sometimes you hear the question, so did Spark kill Hadoop? And this question does not make much sense today. because originally Hadoop was just MapReduce and HDFS, but Hadoop expanded, and there is a whole range of other big data projects under the Hadoop umbrella. So Spark is one of the projects that belongs to this category. And this is really good for us because we can choose the right kind of a project and infrastructure for our big data, and they all belong to this Hadoop family. And we can actually have parts that we can interchangeably use. In some situations, let's say you have the older infrastructure, you will choose to run Hadoop, the old school Hadoop. If you have luxury to buy new machines with a lot of RAM, then you will say, well, Spark is going to be a good choice, and I get the performance improvements. So that is the Spark. Now, what is interesting and what you need to understand for both of these systems, that they are primarily batch systems. And that is, we are going to run some lengthy job. We are going to get a really good throughput. We will be able to process vast amounts of data. But our jobs are going to take significant amount of time. So these jobs may take minutes or even hours when you are dealing with that much data. So the question is now, so how do we address the problem of real time? And this is done with a different category of systems which are known as the streaming systems. And that is something that you need to understand because this is now strongly incoming. It is not only that we want to analyze what happened in the past, but we want to see what is happening right now, and perhaps we want to intervene. So traditional systems are designed in the form where you put your data in the store, and then what you do is you are going to send queries to this data. You're sending the queries, and what you get as the result are going to be some results. And that works for traditional data processing. But if you think what is happening in modern applications, if you are keeping track of what our users are doing, if you perhaps deal with Internet of Things applications, you will see that there is constant flow of data that is coming into our systems. And conventional systems are going to get really busy updating this data, and they will actually not have time to run our queries. So somebody came to the idea to actually invert this whole picture and not to put the data in the data store. But instead, you have your store, and then what you put inside are the queries. And then what you will be streaming over these queries are going to be the data. So you are sending the data here into the system. This data is basically running through the queries, and then at the output you are having the results. Now these results are going to be results for the subset of data that you have seen within certain time frame. So when we talk about these systems, we are thinking about time that is advancing, and then we have a particular window in which we are doing the processing. So you can say, I'm going to do the processing of data within these 4 seconds. And you can do that in blocks. So for example, every 4 seconds, you are going to process the data and get the results. And imagine if you have certain dashboard, the dashboard will refresh then every 4 seconds. So that is one way of dealing with this data. This is called the tumbling window. So the windows of data processing are non-overlapping. But there are also different kinds of windows. There are overlapping windows. So you can say, I'm going to still have the window of the size of 4 seconds, but I'm going to update every second. So this is called the sliding window. And basically, you have the group of windows that are going like this, and that gives you faster response time and faster updates of the results at the end. So systems like this are known as the streaming systems. And they enable us to process the big data that is coming fast into our applications. and we can have a very fast response. There are systems out there that can process this data with a latency of only a couple of milliseconds. And the dominant system in this space is the system called Storm. It is also a system in the Apache family. Apache Storm is heavily used at Twitter, a number of other organizations. And Twitter has recently released an API-compatible replacement with much better performance, sometimes 17 times faster. And that is the system which is called Heron. Same API. And I must say that this programming is particularly suitable for software developers, not so much for traditional data architects and data developers. It requires some good coding skills. And after the first generation of the streaming systems like Apache Storm, people have developed some extensions. And one of the really interesting things is that Apache Spark that we have mentioned just moments ago is also supporting the streaming paradigm. And we have the streaming in that system as well. Now, I told you that Spark is essentially a batch processing system. So how can Spark then handle streaming? Well, Spark actually fakes it by creating small batches. So this is called micro-batching, and these micro-batches will be 500 milliseconds. That is really short. Normally, it is in the range of number of seconds. So 5 seconds, 10 seconds. But you can have the windows that are even going to be an hour or so. So that is a very interesting paradigm. So basically, you are emulating the streaming system by running number of little batches. So that is Spark. Spark is really popular today because it is versatile, it is fast, it can do batch and stream processing. But while the US was busy inventing Hadoop and Spark and a couple of other systems, what were the Europeans doing? The Europeans figured out they need to have their own answer to the big data problem. And they have actually engaged a couple of universities who were actually having tradition of working with highly scalable databases, and particularly database optimizations. And that resulted in a very exciting system, which is also a member of the Apache family. And this is the Apache Flink. So Apache Flink is very similar to Spark when it comes to the way how you use it and the APIs. But one thing that is radically different in Flink is the architecture. Flink is natively streaming architecture. And they fake the batch. So how do they fake the batch? They say batch is just a stream that terminates at some point, which is kind of very neat. And the advantage of Flink is that it will have a faster response time than Spark. And this is really interesting. So why would you care? Now, there are certain scenarios where you cannot just say, well, I'm going to use the micro-batching and replace the streaming. Imagine you are a financial organization and you are dealing with payments. With a system like Flink, you can see what are the payments that are happening right now. You can do quick risk analytics, see who are the parties that are involved, what is their pattern of transactions. And you may determine within a number of milliseconds that this is a fraudulent transaction. With a system like Flink, you're able to intervene and intercept the transaction before it really gets committed, and you are able to prevent fraud. With a system like Spark, another system, you will say, hey, 15 seconds ago, we had a fraudulent transaction. Maybe too late. So the real streaming has its place, and it is important for a number of application areas. So now we have seen Hadoop, we have seen HDFS, we have seen a little bit of MapReduce, we have seen Spark and Flink. Now, there is a range of other systems that are in this space. And recently, one system is getting quite a bit of attention for its practical value. Imagine this. Imagine that you have your enterprise, And in your enterprise, you have a number of systems that may be non-big data systems, perhaps various legacy systems, and they are all producing some data. On the other side, you have systems like either Hadoop or Spark or some other big data systems. So you have the cluster over here that is your big data cluster. So we are going to put it over here, and this is our big data solution. The question is, how are you going to get from data or messages that are being created by these systems, how are you going to get them into these big data systems? And this is kind of quite interesting challenge because sometimes you want to store this data in HDFS, sometimes you want to pass them into the streaming system, but perhaps your streaming system may stop for a while, and then it will start again a number of minutes later, and you want to reread the messages that you did not see in between. So the question is, what do we put here as a bridge that will enable us to nicely integrate these two worlds? And there are a couple of solutions out there. So one of the early solutions for connecting with relational databases is the system called Scoop. Scoop is going to run SQL on the relational database and then get the data and put it in HDFS. There is another system that is called Flume. A Flume is a very capable, actually big data independent system that can take data and files or MQ messages or even Twitter feed from one source and then put it into HDFS or put it in another system. But recently there was one system that is overshadowing them, and this is the system that is developed at LinkedIn, and this is the system that is called Kafka. So this is Apache Kafka. And what they do is they provide something that strongly resembles the messaging infrastructure. So you have queues, and the applications will be sending their data into these queues. And what is interesting is that these queues are supported by persistent storage. So basically, whatever is in these queues will be stored in some type of a persistent storage that can survive the crashes of the system. And then from these queues, we will be feeding the data to our applications. And the nice thing is that the speed of storing the data in these queues is extremely high, and the data is persistent. You can preserve this data depending on your setting. You can say, I'm going to keep them for a month, and then I'm going to purge them. And the system is extremely fast, very lightweight, and the applications have the responsibilities to remember what is the data they need to pull from this infrastructure. So basically, it is a fantastic system as a staging area for your data and integration between different kinds of systems. High performance, lightweight, can preserve the messages, and feed this data into a variety of other systems. So now what we have seen are the top systems in this space. I'm just going to mention a couple of technologies that you typically see for developing of such systems. In Hadoop and big data space, you have a couple of technologies that are quite popular. One is technology called Hive. This is basically your SQL for big data, and it is an excellent starting point for newcomers to the field because they will feel, well, this is really working like some type of a database. There is a SQL, it has certain limitations, but you can transfer many of your existing skills. There is a technology called Pig. Pig is a language that is particularly suitable for ETL type of jobs. And people usually combine Hive for some tasks and Pig for the other tasks. Usually ETL type of stuff is a really good match for Pig. There is a solution which is called Scalding. Scalding is the Scala API for Hadoop, and Scala is a programming language that runs on JVM. It's compatible with Java, And it is the next development of Java, if you want. Very powerful language. Most of the Twitter is implemented in Scala, LinkedIn, Spotify, a number of other companies are using it. And aside of that, we have a Spark. And the Spark is typically programmed in Scala. One of the great advantages of Scala, for example, over Java for development is that Scala code tends to be much shorter. Sometimes we can condense 60 lines of Java into only 3 lines of Scala. And these lines are very natural to read, very, very easy to understand, and a good match for the problem domain. And recently, you also see a couple of other languages. So there is the Python that is usually lagging a little bit behind. The language is easy to use, but often lacks the features that we see in the Scala API. And data scientists sometimes use the language called R. R is a language that is suitable for various mathematical operations. And once you figure out how to do things, then you would typically code it in some other system. So I am going to finish this presentation with a set of steps that I want you to do to be successful with your data. So I will advance all the way to the end of my presentation. And I will conclude with these points for getting, I want to show you before just one picture. And that is, what can you expect to see in your enterprise? You expect to see integration. So you have your traditional systems, your traditional warehouses. You have at the bottom a variety of big data systems. So this is Hadoop, a variety of other NoSQL stores. You typically integrate the data with your traditional warehouse. So you will have some feed of data from your Hadoop systems into the conventional warehouse, where you can then do the analytics and business reporting. And then you have the streams that are providing you the real-time insight and also integrate with both these big data and conventional systems. Lambda architecture is something that will enable you to combine the real-time and the batch processing. So you get the real-time insight plus the wisdom of previous applications. Now, when you want to be successful with big data, you should not immediately fall in love with the technology so much that you become disinterested in business problems. Always look, what are the business problems and how can you solve these business problems with these technologies? So always deliver tangible values to clients. And this seems obvious, but sometimes the teams, the geeks, so much fell in love that they don't care about customers anymore. They just want to play with new technology. So you need to watch this carefully. Always work on something tangible. Governance is hugely important for big data. It is even more important than for conventional systems. But don't make the mistake like some companies. They think about governance now for 3 years. They don't have a single big data application, but they are all getting ready for governance. This is not good. Start small, get some pilot projects, and then introduce a lightweight form of governance that will not prevent the innovation. Prioritize. Do something that is really important for the business. Do something like that first. And always, always integrate with existing IT. So never make your big data systems be an isolated island. When you start working with big data, your existing teams are likely not to have much knowledge in big data. And this is fine. It is OK to say, I don't know. What is not OK is, I don't want to learn. So you grow your champions, your teams. Sometimes you get external help, mentors, or even hire people, and make sure that you have a real champions for big data in your organization. And finally, field is immature. Every 6 months, there is something new and exciting, so you need to be on the lookout. Things that we thought don't work so well may be fixed in 6 months, so you need to watch for this. Always keep an eye on. And I think we are out of time. I'll be open for questions. I'll hang around after the talk, and thank you so much.